this discussion, you'll be introduced to the concept of probability distributions, specifically discrete distributions and their probabilities. First, we'll talk about random variables and probability distributions. If you recall, an experiment is any process that leads to one of several possible outcomes. So the random variable is just a mathematical way of describing these outcomes. And when we plot the probability of all the random variables on a graph, then this graph is what we call probability distribution. So the random variable and probability distribution are two related concepts, and we'll learn about both of them in much more detail. The next concept that we'll see is that of expected value and variance. This is very similar to what we calculated in the form of mean and variance for a population or a sample. The only difference being that you'll learn how to calculate the same for a probability distribution. Expected value is generally used to find an anticipated value for an investment at some point in the future and is popularly used in industries like insurance and card games. We'll see some interesting applications around expected value. Apart from that, you'll also learn about the important discrete probability distributions that might come across in your day-to-day applications, more specifically the binomial distribution. Binomial distribution could be used to mimic experiments like public votes in an election survey or analyzing new products response via a limited launch. Random variables part 1. I'm quite sure that you have heard this well-known saying about casinos that the house always wins. What it means is that the casino gambling machines and games are designed in such a way that in the long run casinos always make money. One or two people may end up winning large sums of money, but the machines are designed such that the rest of the people collectively lose more. So how do the casinos ensure that the house always wins? It is quite simple. They use probabilities. In fact, casinos use a very basic concept of probability to ensure a win for themselves. Do we wonder how? To understand this, let me tell you about a simple gambling game we can play. We can take a bag and fill it up with 3 balls, 2 red and 1 blue. Each participant had to take out a ball, note its color and then put it back in. This process was followed until each participant has taken out a ball from the bag 4 times. A participant who got a red ball all 4 times would receive 150 rupees from the house. Attractive offer, isn't it? However, the participant who got any other result would have to put or pay 10 rupees. So would you play or would you like to play this game? Is this the kind of game in which we, the house, should always win in the long run? Or are we going to incur some losses in the long run? In order to understand all this, we'll approach the problem in 3 steps. First, we'll see what all kinds of combinations can come up. Then we'll see how likely each of these combinations, that is what their probability is. Then we'll see how we can use these probabilities to estimate the profit and loss of a player he would get on playing the game once. Let's go through the various outcomes possible after a participant has tried the bet. As you would guess, the one outcome our players would want the most is that all 4 balls end up being red. However, that is not the only possible outcome. They could, for example, get 3 red balls in a row only to find that the last ball is sadly a blue one. Wouldn't that be sad? So can you find out all the possible outcomes? So let's first list down all the possible outcomes one by one. We could get 4 blue balls. There's only one outcome in which this happens. We could get 3 blue balls and 1 red ball. This could happen in 4 ways: R triple B, BR double B, double BRB, and triple BR. We could also get 2 blue balls and 2 red balls. This could happen in 6 ways. Also, we could get 1 blue ball and 3 red balls in 4 ways. And there's only one way in which we could get 4 red balls. So in total, there are 16 possible outcomes. Random variables part 2. Let us go back to some of the original questions that we were concerned with, starting with how likely is the house to win, or what is the profit or loss you should expect while running such a business. However, currently we cannot answer these questions, and in order to answer them, we need to analyze the outcomes in terms of probabilities. For example, if the probability of getting 4 red balls in a row comes out to be extremely low, we may say that the house is likely to win. On the other hand, if the probability of getting 4 red balls is comparable to the other possible outcomes, it may be profitable for the players. Let us think about how we can do that. So there are various ways in which we can convert these outcomes to numbers, or in other words, quantify them. Let's assign the value of the number we get after quantifying to a variable x. For example, let's quantify the outcomes by using the number of red balls. So instead of saying that the outcome is blue, red, 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 we can say that we got 3 red balls and x equal to 3. Similarly, for the outcome blue, red, we can say x equal to 2. As you can see, this number used for quantifying outcomes is really important. In statistical language, it is known as random variable and is denoted by uppercase X. It is basically any variable that converts an outcome to a number. Another important question is, are there more ways in which random variable x could be defined? We can define x as the number of blue balls that we drew from the bag, or the number of red balls minus the number of blue balls that we have drawn from the bag. So the question that now arises is, which is the correct random variable? Out of all these options that you have, which one should you choose? Well, the answer actually depends on the information you are interested in. In our example, we are interested in the number of red balls. Recall that if the player draws 4 red balls, he or she wins 150 rupees. However, if the player draws even 3, 2, 1 or 0 red balls, he or she loses 10 rupees. So let's define x this way, x equal to number of red balls. Now if we want to find whether we will actually make money or lose it, we need to know how likely the different values of x are. What is the probability of each value? We'll see that in the subsequent discussions. Probability distributions. Let us see the different values of the random variable x as we defined before. It will take for all the possible outcomes of our game. Remember that x was defined as the number of red balls that we have drawn from the bag. So if the possible outcome that we look at is the one with 4 blue balls, obviously x takes the value 0. For all 4 outcomes where we only drew 1 red ball out of the 4, x will take value of 1. For the 6 possible outcomes where there are 2 red balls and 2 blue balls in the various combinations, x will take a value of 2. For these 4 outcomes where we have 3 red balls and 1 blue ball, x will take the value 3. And for the last outcome where we have 4 red balls, x takes the value of 4. So basically, by doing this, we have brought our 16 outcomes into 5 groups where the random variable takes values from 0 to 4. Now, if you want to find out whether we will make or lose money in the long run, you need to find out the likelihood of each of these values occurring. But how to do that? Let us say that we conducted experiment with certain 100 individuals who played this gamble. Based on each person's response, we put a small note on a chart. For example, person A got 3 red balls, so we put a note with his name on the chart over value 3. Similarly, person B got 2 red balls, so we put a note with his name over the value 2. This way, as more and more people play, we will fill up the chart accordingly until we have responses of all the 100 people on this chart. So in this chart over here, on the x-axis we have random variable x from value 0 to 4. On the y-axis we have the frequency, the number of times the random variable appeared in our experiment. So this chart is called a histogram. So the heights of these bars in this plot correspond to the number of times the frequency of that random variable appeared in our experiment. For example, 2 out of the 100 people drew no red balls, 10 out of the 100 people drew 1 red ball, and so on. So recall that the probability of any outcome is the number of favorable outcomes divided by the total number of outcomes. So let's find the probability that our random variable x takes the value 2. The number of favorable outcomes in this case will be the number of people who drew 2 red balls, and that number is 32. The total number of possible outcomes is 100, as that is the total number of people who participated in that game. So the probability of drawing 2 red balls is 32 by 100, which is equal to 0.32 or 32%. So we can extend this probability calculation for all the different values of x and put all of this information in a single table as shown here. After calculating the probabilities for x equal to 0, 1, 2, 3 and 4, we get the probability that x is equal to 0.02. The probability that the random variable x takes a value of 1 is 0.07. The probability that x takes a value of 2 is 0.32. Probability that x takes the value 3 is 0.43. And for x equal to 4, the probability is 0.16. Now, this table here is called the probability distribution, as it tells us the probability of all the possible values of x. So now we will take these probability values and just draw them in a chart to aid our understanding of the probability values. On the x-axis here we have 5 random variable values, and on the y-axis we have our probability values. The chart here where we plot our probability values versus the random variable values is called the probability distribution chart. So as you can see, the probability distribution when displayed in the form of a bar chart look exactly like our original histogram, just with a different scale. That is, since probabilities can lie between 0 and 1 only, the values on the y-axis are now restricted in the range of 0 and 1. Each value here represents the probability of getting a certain number of red balls. So this is what our probability distribution looks like in tabular form and in bar chart form. As you can see clearly from this example, a bar chart gives us a much better visual idea of what the probability will be. Hence, this form is more commonly used. Now, we can use this distribution which gives us how likely each value of x is and find the answer to our original question, that is, would we in long run make money or lose money. So if we recall from our office game setup, we fixed our random variable x as the number of red balls we got in the experiment. We then made a probability distribution for x, which will help us to see how likely each of these values of x is to happen. Now, as we said earlier, we want to use probability and find whether in the long term the game or a bet will be profitable to us, the house, or not. Question is, how will we do that? Let us see. Suppose 1000 people are playing this game. How much do you think an average person would win or lose in this game? Can you try and take a guess? So for these 1000 people, do you think you'll be able to tell me how many people are expected to draw one red ball? How many people are expected to draw two red balls, three red balls, and four red balls? As you remember from before, we know that the probability that x is equal to 1 is the value 0.07. So multiplying that by 1000 will give us the expected number of players who will draw one red ball. 1000 times 0.07 gives us 70. So in other words, about 70 people will draw one red ball out of those four balls. Similarly, the probability that x is equal to 2 will be 0.32. So multiplying by 1000 gives you 320. So again, it means that 320 players on average would draw two red balls. Similarly, for x equal to 0, 1000 times 0.02, which gives us 20 people who will draw 0 red balls. 430 people will draw 3 red balls and 160 will draw 4 red balls. In other words, 160 people on average will win this game. Question is, so how many red balls are we expecting to see on average in our game? Remember, 1000 people played this game and out of those 1000, 70 people had drawn one red ball. Similarly, 320 people drew two red balls. 0 balls were drawn for 20 people, 3 balls by 430 people, and 4 balls by 160 people. So I can say that the total number of red balls we'll get after 1000 attempts at the game will be 0 into 20, 1 into 70, 2 into 320, 3 into 430 plus 4 into 160. The sum of all these events gives us 2640 red balls. So basically we saw 2640 times a red ball in our 1000 experiments. So if we take the division of these two, we can say that we are seeing 2.64 red balls in one experiment on average. In other words, we can expect a person to draw 2.64 red balls in one game. And so in nutshell, the average value that we would expect to get for a random variable is called its expected value. Let's continue our discussion of expected value. Let's now formally define the expected value. Let's say that a random variable x can take values x1, x2, x3 and so on till xn. The expected value of this random variable x would be given by the expression expected value equal to x1 times probability of x1 plus x2 times probability of x2 plus x3 times probability of x3 and so on till xn times pxn. And remember, probability of x equals to xi denotes the probability that the random variable x takes the value xi. In our example, the value that the random variable x can take 0, 1, 2, 3 and 4. So the expected value of this random variable would be given by the expression expected value equal to 0 into probability of 0 plus 1 into probability of getting x as 1, 2 into probability of getting x as 2 plus 3 into probability of getting x as 3 plus 4 into probability of getting x as 4. We have already computed these probabilities before and plugging those values. We get the expected value as 0 into 0.02 plus 1 into 0.07 plus 2 into 0.32 plus 3 into 0.43 plus 4 into 0.16 equal to 2.64. So again, the expected value for random variable x, that is the number of red balls, is 2.64. However, I am sure you are wondering how can you get 2.64 balls in one attempt. The number of balls would be 2 or 3, where we are saying that on average we expect to get 2.64 balls. Actually, it is not unusual to have an expected value that may never actually come up. We say that the expected value is 2.64. It doesn't mean that we expect to get red balls in an attempt that many 2.64 balls. What does this value actually means? Is that if you were to play a game infinite number of times, then the average number of red balls you would get is 2.64. But does this value really even help us with our question? We still can't tell whether we would make money or lose in the long run. So what should we have done differently to answer our primary question? If you want to find out whether the house would make or lose money in the long run, then we would need a different random variable. Probably a better random variable here would be the amount won after playing the game. Let's continue our discussion of expected value. So let's define our random variable this way. X equal to money won after playing the game once. This definition of X works well for us if we get a high expected value for it. That would imply that on average, players will win a lot of money in our game, which is obviously not a good thing for us. On the other hand, a low expected value here would mean that on average, the players don't win a lot of money. So for this new random variable, X can take two values, -10 and +150. This is because player wins $150 for getting 4 red balls and loses $10 for getting any other outcome. We know that the probability when X takes the value 150 is the probability of getting 4 red balls is equal to 0.16. On the other hand, the probability of losing the game when the random variable would take the value -10 is 0.84, which is the probability of getting any other possible combination of balls, namely getting 0, 1, 2 or 3 red balls. So we can go ahead and compute the probabilities of getting 0, 1, 2, 3 red balls. We could get the probability of getting 0, 1, 2, 3 red balls by adding these individual probabilities 0.02 plus 0.07 plus 0.32 plus 0.43, which is equal to 0.84. In other words, the probability that a player will lose this game is 0.84. Applying the same definition of expected value as we saw before, we can compute the expected value for this event as 150 into 0.16 minus 10 into 0.84, which is equal to $15.6. What this means is that on average, a player would expect to win $15.6 by playing the game. So it turns out that the game is a disaster for the house. If you want to make money, you need to ensure that the expected value for the money won by a player is negative. This is to ensure that players lose money and the house wins in the long run. So how can you do this? You can decrease the prize money, increase the penalty, or just decrease our players' chances of winning. Any of these choices will decrease the player's expected earnings from the game. We can go ahead and fill in our rules and configuration of the game. So you can now understand how casinos ensure that they remain profitable. The casino machines are all designed in such a way that the expected value of the money earned by the player is always negative. This means if we design the game such that the expected value of the money earned by a player is, for example, -10 or -$20, we can be fairly confident that the house will be profitable. Let's look at one real life example of the expected value. We know that the expected value is the basis for insurance companies, and we can do a simple example based on this concept. Based on certain sources, the company estimates that the probability that an accident will occur within the next year is 0.00071. On the basis of this information, what premium should the insurance company charge to break even on a $400,000 on a 1-year term policy? So let us try to calculate the expected value that the company will need to pay to settle a policy. In case of an event of an accident, the probability is 0.00071 and the amount to be paid is $4 lakh. However, in case of no accident, the probability becomes 1 minus 0.00071, which is equal to 0.99929, and in this case, the amount to be paid is 0. Thus, the expected value will be x times probability of x when there is no accident plus x times probability of x when an accident occurs. In case of no accident, x times probability of x becomes 0 times 0.99929, which is 0, as shown in the table here. And in case of an accident, x time probability of x becomes 0.00071 times $4 lakh, which is approximately $284. These computations are provided in the table. Thus, on average, the company needs to pay about $284 to settle a policy. Thus, the premium should be $284 plus whatever return the company needs to cover such administrative overhead and profits. Variance. We can calculate the expected value if we are given a random variable and its corresponding probability distribution. So this answers our question about the central tendency of the distribution. However, you also learned that apart from the central tendency, we also look at the spread or variability of the data. So let's go back to some of our previous example where we created a probability distribution of the random variable x, where x is the number of red balls in the bag. We want to find out the variance of x. To calculate the variance, we have a very simple formula for doing so. Basically, it is variance of x equal to x minus mu raised to the power 2 times probability of x summed over all the values of x, or alternatively summation of x minus mu raised to the power 2 into probability of x equal to xi, where mu, or sometimes called as x bar or expected value of mean of the random variable. Recall that for x equal to 0, the probability was 0.02, for x equal to 1, it was 0.07, for x equal to 2 it was 0.32, and for x equal to 3 it was 0.43, and for x equal to 4 it was 0.16. Here mu denotes the expected value that we had earlier calculated. So it will be the expected value of the number of red balls, which we calculated to be 2.64. So to calculate the variance of x, it will be 0 minus 2.64 raised to the power 2 into 0.02 plus 1 minus 2.64 raised to the power 2 into 0.07 plus 2 minus 2.64 raised to the power 2 into 0.32 plus 0 minus 2.64 raised to the power 2 times 0.43 plus 4 minus 2.64 raised to the power 2 into 0.16, which sums up to 0.8104. Thus, the variance of this distribution is 0.8104, and the standard deviation will be the root of 0.8104, which would be 0.9002. Calculating the variance could be used to compare the spread of different probability distributions